If we know the derivative of g of x and r of x, would it be possible to know the derivative of f of x if f of x is equal to g of r of x? In order to answer this question, I will implore you to use the power of your imagination. Let us now imagine that we are looking at a ball rolling across the street in front of us. We can see that the motion of the ball is constant, and we may say that the ball position is equal to some constant c multiplied by time. More formally, it could be written as p equals c times x, where x represents time, and this will be our function g of x. The rate of change of the ball movement, or rather its derivative, in this case is simply equal to c. At this point, we shall engage our imagination 100% and pull out of our pockets a device which slows down time so that everything looks like it's moving in slow motion. We shall turn the dial to slow down world time by a factor of 2. More formally, we can write this down as world time is equal to 1/2 of our time, and this can be our function r of x. The derivative of such a function is 1/2. We can see that this slows down the ball movement by twice as much. Formally stated, the relationship describing the position of the ball in our time happens to be p equals to c times 1/2 times our time, or g of r of x. The derivative of this function is c times 1/2. This example seems to imply that in the situations where our function is g of r of x, our derivative would be equal to the derivative of g times the derivative of r. This seems too simple, and at this point, it is very questionable if this relationship generalizes to all functions. The first concern is that these functions are simple and linear, and not some complicated functions with many hills and valleys. To address this, we must understand that when we are looking for a derivative at a particular point, then all of the complexity of the function and the shape of the curve in other locations doesn't really matter. If we zoom into the local neighborhood, the function should have an appearance of a nearly straight sloped line. The derivative is the measure of how sloped the line is at that point. If we are watching the ball drop from a building instead of roll across the street, we will notice that the ball picks up speed as it falls, and its derivative, the rate of change of its position, is different at different times. If we can slow down time by a factor of 2, however, and then zoom in to inspect how this affects each neighborhood along the modified curve representing the change of the ball position over time, we will notice that each slope is now twice as shallow, and for this reason, the derivative of the final function is twice as small. Even if the curve describing the motion is far more complex than the one describing a falling ball, we could still say that the derivative describing the motion of such an object would be half as large if we would slow down time by a factor of 2. It must be noted that a problem with our previous assumption becomes apparent in this example. The previous example led us to conclude that the derivative of f of x is equal to the derivative of g of x times the derivative of r of x. However, this was concluded in a situation where both the derivative of g of x and the derivative of r of x remained constant for all values of x. In this example, the derivative of g of x changes with time, and since we are looking at the rate of change of g of x at our point in time, which has gone twice as far ahead of the world time, it is not the point in time that the ball is actually experiencing. We should disregard the derivative of g of x, which tells us the rate of change of the ball position in our time, and instead consider the derivative of g of r of x. That describes how the ball position changes at a point in world time that corresponds to our point in time. This means that the derivative of f of x is actually now equal to the derivative of g of r of x times the derivative of r of x. Although we allowed the function describing the position of the object to become complicated, we still kept the function describing the change between our time and world time to be very simple and its derivative the same at all times. If we complicate the mechanism by which we alter the motion of time, and time doesn't simply slow down, but maybe slows down at an increasing rate, or slows down and then speeds up, or maybe even goes backwards, then we have a more general description of the function r of x. It is important to note that regardless of what our time-altering function looks like, we will consider what effect it has by zooming in to examine its time-altering properties at a particular moment, and we will find out that if we zoom in far enough, the change in how the time is slowing down, speeding up, or going backwards is actually linear. That is to say, that if we are looking from the perspective of our time, we can see that the world time is moving at a different and steady pace, and that in the very near future point of our time, the world time will also change by a small amount. If we zoom in far enough, we should even be able to say that these relationships are nearly linear. This means that when we zoom in, then for a small change in our time, say 2 microseconds, the world time at that point will change by 5 microseconds. If the small change in our time is twice as big, say 4 microseconds, then the world time should change by 10 microseconds. At a different point of our time, the relationship could easily be different. Say 3 microseconds in our time is 1 microsecond in world time, or even negative 1 microsecond in world time, if the world has started to move backwards in time. This relationship is in a sense described by the derivative function. So what we are saying is that at every point in our time, the derivative of the time-changing function will describe how fast the world time is going. We already know what effect does the time slowdown or speed up have on the derivative of the function describing the object position. If the speed of world time at a particular moment is half of our speed, then the object will move half as fast. And if the speed of world time is twice as fast, then the object will move twice as fast as well. If the speed of time is negative, which is to say that the time is going backwards, then the object will move backwards, and the change in position will be in the opposite direction of what it should be. In all these examples, it is important to recognize that the speed of time, represented by the derivative of r of x, is multiplied by the rate of change of the position of the object, represented by the derivative of g of x, at the relevant point in the world time given by r of x. Since the derivative of our time change function tells us how quickly time is changing in the world at a particular point in our time, we can simply multiply that value with the change in the position of the object at the corresponding point in world time in order to find out the change in position at a particular point in our time. This is another way of saying that in general, if we have f of x equal to g of r of x, then at any point of x, we can multiply the derivative of g of r of x by the derivative of r of x in order to find out the derivative of f of x. Therefore, it can be concluded that if f of x equals g of r of x, then the derivative of f of x is equal to the derivative of g of r of x times the derivative of r of x.